So here we go. We are going to start by drawing 2 points on your circle, labeling them B and C. You do not have to draw them in the exact same spot as me. That is okay. And for this part, I'm just going to use my regular pencil. I'm going to draw B and C just so that they're not like on total opposite sides of each other. So I'm just going to put, I don't know, B here and C here. So it doesn't really matter where they go, but the activity I don't think is as visually pleasing if you put them on direct opposites of each other. It should still work, but I don't like it as much. So Lucas, you'll want your note out, and then we got 3 colored pencils and a protractor after this part.
Black will be fine.
And then it says draw in angle BAC. So I'm going to use my first color to draw in angle BAC, and A is the center point. Now again, your B and C do not have to be in the same spot as mine for this activity to work. As long as you can measure an angle, you should still be okay. So you're going to draw B and a C. You can make it look like mine if you prefer. And then you're going to draw in angle BAC in one of your colors. You don't have to use colors. I just think that the activity, again, is visually pleasing when you have 3 different colors. And I'm going to find that measure. Now again, my measure might be different than yours, and that's okay for this activity. The overall concept should still apply. So as a reminder, when you are using a protractor, that little center notch goes at the center of the angle, and one of your angle sides should be lining up with one of your zeros. Now since I'm lining it up to the right, that's where I start with my 0, and then I work my way up to the angle. I need to extend my angle ever so slightly here because I can't really tell what it is. So 1 second. And mine is not at a super pretty spot. That's okay. I'm just going to estimate it a little bit here. Mine looks to be at about 83, personally. All right, so I'm going to leave that right there for a second. If you need any help measuring an angle, please ask somebody around you. Or I guess you can ask me too. And angles that have a vertex at the center like that are called what kind of angles again?
Central angle.
Central angles. So we call this a central angle. That's going to go on that first blank up there. We call this a central angle. And then it asks for the measure of arc BC. Well, we learned in section 2 that if your vertex is at the center, then your arc is exactly the same as your angle. So it would be exactly 83 degrees. So I would like to take a moment to pause and just make sure I don't move on until everybody's on the same page as me. Now again, yours might not be exactly 83, and that's okay. The activity should still work, so I want you to use the measure that yours actually is. Okay? Step 4. Draw a third point of the circle and label it D. I want you to watch this first because in years past people have done this part incorrectly. So I'm going to put a point here, D, and I'm just going to not put it between B and C. Again, you can, but it's not going to be as visually pleasing if you do. So I'm going to put my point D somewhere on this major arc. It doesn't really matter where. So I'll put point D right there. And I'm going to draw in a different color now. So I'm going to grab my second color, angle BDC. So be careful here. We're going to connect B to D and then D to C. So it's okay if there's some overlap. It's okay if they should kind of overlap or cross a little bit. It's okay if the sides overlap. It's okay if they don't overlap. That's fine. But I want you to draw a point D on the circle somewhere like on the outside of B and C, not between. And then draw angle BDC, which has nothing to do with A. It may go through A potentially, but so I'm I'm using my second color just so that visually I'm differentiating between the two, especially since there will be a little bit of overlap. You don't have to use colors, but. And then I want you to find the measure of that angle.
The angle from D to B.
Angle D. So we drew an angle BDC, and then I want you to find angle D. Now, central angles, like the red one, have a vertex at the center. Where's the vertex of this green angle, angle BDC? It's not at the center. Where is it? Some trick question for Howard, Kaden. On the circle. So when you have an angle with the vertex on the circle like that, on the outside of the circle, we call that an inscribed angle. So that's what we're going to be talking about today, inscribed angles, which are different than central angles. Now look at mine for a second. What appears to be the relationship between angle D, 41.5, and my arc BC? Cody?
Arc BC is double angle D.
Okay. So angle BDC is half. Measure arc BC. Or what he said was measure arc BC was 2 times measure angle BDC. And that will always happen. So yours should be somewhat close. Whatever your arc was for BC, this should be exactly half or somewhere very close. And if it's not, we are doing something incorrect. So let me come over.
Yeah.
That could just be human error.
It's okay if it's 1 or 2 degrees off, yeah. Because that's just either you drew it maybe wrong or, but it shouldn't be like super far off. I'm just going to make sure this one's correct. 92 is probably not right. That one to me looks like it's closer to about 46. Anybody else nowhere close? 5 degrees off. I would not say that's 85 degrees. I would say that's probably closer to like 81 or 2. And then that's like 41. So I think it's probably closer to like 41 BD2. I would say this is probably closer to about 60, and you're about right. A lot of it's just you guys aren't reading your protractor correctly, but it should be exactly half, or very, very close. Now, the next thing I'm going to do is draw one more point on the circle and label it E, so just somewhere, it doesn't really matter where. And then finally take my third color and draw in angle BEC. So put a point E somewhere on the circle, again, preferably not between B and C, and then draw in angle BEC. It's okay if it doesn't go through A. Last color, yep. So you should have 3 colored angles on there. And then it says find the measure of that angle. Man, mine again is just about. And what appears to be the relationship between angle D and angle E? The same, or they should be really darn close. Okay, so they look like they're probably congruent to one another. Now I'm going to tell you why this makes sense. This angle BDC intersected arc BC. Hey, that's rude. It was exactly half of it. Okay, so angle BDC intersected this arc and was exactly half of it. While my blue angle intersects the exact same arc and is also half of it. So anytime you have two inscribed angles that are crossing the same arc, they're both half of that measure and therefore congruent. So I could draw even another point connected to B and C. That one would also be 41.5. I could do another one here. I could do another one here. There's infinitely many angles I could create that are all going to be 41.5 degrees. Good, and those are our two big lessons of the day. So you can set aside the protractor and the colored pencils. So the first thing we talked about, an inscribed angle, is an angle whose vertex, like Caden said, is on the circle. So that's different than a central angle. I think it was someone in here yesterday that said, aren't all angles central angles? No. The center, or the vertex of the angle does not have to be at the center. It doesn't even have to be on the circle. It could be anywhere on the circle. But if it's on the circle, we call it an inscribed angle whose sides are chords of the circle. So something like this angle ABC right here. That would be an inscribed angle because the vertex is on the circle. And the intercepted arc, you're going to hear me refer to that today quite often, is the arc that it crosses. Now, first hour, I have so quiet in there, but I have one person who does such a great job of asking fantastic questions. And she asked, this intercepted arc, I don't understand this. So I said, okay, what if I extended these sides a little bit? And do you see how it like closes off this portion of the circle when you extend out the sides? That's the intercepted arc. So if you kept the sides going, you're kind of asking yourself, what snippet of the circle is it cutting off? And that's your intercepted arc. Huh?
That's what
Good. I'm glad. And the inscribed angle, that's a typo, not angel. Inscribed angle is always 1/2 of the measure of its intercepted arc. So for example, if this angle here was 60 degrees, just making it up, then arc AB would be 120. So that's different from central angles. Central angles were exactly equal. Inscribed angles are half. Now to me, again, this makes sense because it's kind of like you took the central angle and you pulled it back like a rubber band. And when you do that, you have this stretch happening that makes it really, really narrow. So the fact that it doesn't equal the same thing as the central angle makes sense to me because it's like you took that and you were like, going to pull it back further and then that angle gets narrower. So your inscribed angles are always exactly half of the arc that they intersect. And then we just talked about this. If you have two separate angles, so here's an angle, and here's an angle, that intersect the exact same arc, and they're inscribed, then they're both half of that arc and automatically congruent. So if you have two separate, or however many, inscribed angles that intersect the same arc, then those angles have to be congruent to one another. So if you knew, again, that this was 40 degrees, well then this one has to be 40 as well, because they're both half of the arc, which would be 80. Question?
So the inscribed angle always shares the two endpoints, but has a different third point?
Always shares the two endpoints, but has a
Like,
different third point.
On the
For this theorem?
Like on the one we drew, the three colors, they,
Yeah, like this
all
one,
three
yes.
of them share BC,
Yeah.
but they have different middle points. Like the third point, like
The vertex is different. I did that on purpose. So like they don't have to always share an intercepted arc, but if they do, then they're always congruent to one another. If they're inscribed. Did that answer your question?
yes.
examples in the back here. Now, first of all, I think again it was this class, it's a great question. This is a diameter. Sometimes they tell you straight up, hey, this is a diameter, which is helpful. If they don't and you're ever questioning, you can always come ask me. But if you see a straight line segment that goes to the center, it's most likely a diameter. All right, the first thing we're going to find here is angle T. So angle T is intersecting this arc RS, and its vertex is on the circle. So that means that angle T is exactly half of the arc that it intersects. So in this case, 48. And what's half of 48? 24. 24. Because inscribed angles are always exactly half of the arcs that they intersect or open up to. Okay, measure arc QR is the next thing we're going to find here. Now, QR doesn't have any angles opening up to it, but we do have an angle right here. That's 50. So let me first ask you, how big would arc QT be? 100, double the 50. And then, because we have a diameter and we have half of the circle, we just have to do 180 minus 100, which is 80. Example 2 says, given the fact that angle E is 75 degrees, find angle F. So here's angle E, opening up to lovely arc GH. And here's angle F. Well, you have two different inscribed angles that are both opening up to the same arc. Therefore, they automatically have to be congruent to one another, and angle F has to be 75 degrees. Now, you can go the long route here. You can say, okay, if this is 75, then the arc is double that, 150. And if the arc is 150, then angle F is half of that, 75. But you're just doing more work than you need to. If you see two inscribed angles opening up to the same arc, they are always the same measure. Questions on those two? Okay, I would like you to do these three. It is difficult to find the red arc or angle when your papers are black and white, so I will go ahead and color this for you. So you're going to find that angle measure, angle G, for me. I'm going to have you find arc TF for me, and I'm going to have you find angle X for me, please. Go ahead and take a moment to do those three problems. We're good? Who can tell me they got for number 1? Jacob? 45 degrees, half of 90, very good. How about number 2? Jensen?
It would be 76.
76, double the 38, very good. How about number 3? Cody S.
72 degrees.
72 degrees, very good. Exactly equal to the inner angle. Awesome. And you also, again, you guys are at an age now where you can always ask yourself if your answers make sense. So make sure that your answer looks like the picture. So if it doesn't look like it's 45, then something's wrong, right? Unless we have crappy problems and don't have it drawn correctly. All right, questions on any of that? Lovely. 2 theorems left, then we're going to be done. Inscribed polygons. I was telling first hour that I didn't do a ton with inscribed polygons until I was in college, and I had to take this crazy geometry course where we did all kinds of stuff with shapes inside of circles, some 3-dimensional, some 2-dimensional, so on and so forth. So you're not going to do a ton with these inscribed polygons now, but I'm going to tell you right now, you never know what kind of classes your college majors will make you take. I'm just going to throw that out there because I had to take this crazy computer class that I've never used a day in my life. But inscribed polygons is a polygon where all of the vertices are on the circle. So I tell people it's almost like the circle is a force field. And you refer to that circle as being circumscribed around the shape. Now, we did talk about these two words, and we talked about in chapter 6, the triangles. I mentioned them, but I just told you weren't going to have to do a lot with that. Probably still the same thing except for these two theorems, but still a good word to know. So our first theorem here, if we read through it, says if a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle and vice versa. So this means that if this angle is a right angle, and we have a nice little right triangle here, so that angle equals 90 degrees, then AC has to be a diameter. And here's why this should make sense to you now that you know what an inscribed angle measure is. If that angle is a right angle, then it's half of the arc that it opens up to. Well, that would mean that this arc is 180 degrees, and therefore A to C is cutting your circle in half into a semicircle. So anytime you see a diameter and an angle opening up to a diameter, it's automatically going to be a right angle. So something like letter A down here as the example, if you know this is a diameter, a chord going through the center, and you have an inscribed angle opening up to that diameter, then that means angle C has to equal 90 degrees. And therefore 2x equals 90 and x equals 45. So any angle that opens up to a diameter, I think there's one problem on your test like that. We just kind of finished writing the test, or reorganizing it, I should say.
So, could you, if you moved like B, like say like down or up, would it still make that 90-degree angle? Like if you move point B like around a circle?
No, because unless you moved A and B. So if I moved A and B, and so it was still a straight line, then yes. But if I only moved B, sorry, that was loud. If I only moved B, then that's no longer a diameter. So no, that rule wouldn't apply anymore. Okay, my second theorem here.
Well, no, I was talking about the first one. Sorry.
Huh?
Do you see how the first one's that's not the?
Oh, you can move B.
Okay.
I'm sorry. So yeah, so like if B was here,
Yeah.
and then it
would
opened
still
up
be
to.
90 degrees.
Yep,
Okay.
Yep, because again, it goes back to that rule that if it opens up to the same arc, then it's the same measure. Very good question. Okay, second theorem here says a quadrilateral can be inscribed in a circle if and only if, meaning it's biconditional, works both ways, its opposite angles are supplementary. So first of all, we're talking specifically about a quadrilateral. What makes something a quadrilateral? You can do it, fourth hour. What's a quadrilateral? Has four sides. That's all it means. Four sides. So no specifications after that. So if you have a quadrilateral where all four vertices of the shape are on the circle, meaning it's inscribed in the circle, then its opposite angles are supplementary. So in this case, that would mean that angle E and angle G add up to 180, and angle F and angle D add up to 180. Now again, because I know some people in this room are like me and analyze everything, I want to show you why this makes sense. Angle E opens up to all of this arc, from F through G to D. You see that? On the flip side, the opposite angle, angle G, opens up to all of this. So together, they open up to the full circle, which is 360, and half of that is 180. So that's why those two angles together have to add up to 180 every single time, because they're exactly half of their arcs. Okay, but if you just want to memorize the nitty-gritty of it, you just have to memorize that the opposite angles equal 180. So we don't need to go through all of this, but something like B, for example, and I know there's a test question, and every year people miss this because they just didn't memorize the theorem. That's it. It's not a hard concept. You just didn't memorize it. So if you see that quadrilateral, then the opposite angles have to add up to 180. B and D are opposites, so x plus 82 equals 180, and then you would solve. So y equals 112. Check my math. I'm very tired today. X equals 98. I think. Okay. I want you to do just A really quick for me on your own. I want to see if you can find X and Y. You can raise your hand and tell me what X is. Reese?
90 degrees.
90 degrees, because it opens up to a diameter. Perfect. And therefore, Y would have to be how big? 50. Very good. Just subtracting from 180. Awesome. Okay. So your homework, I want you to listen very carefully to me, because first hour I said it, and then they kind of just ignored me, which is fine. It's their choice. But your homework is technically only 10.4, which is actually quite short, because it's just one page. All right? So that's your homework, the practice problems of 10.4, for you to be caught up on everything. I do think some of you are going to finish this early, and if you do, I think it would be wise of you to start your quiz review, because the quiz review is pretty long, and I think if you wait until Monday night to do it all at once, I think you will not get it all completed. So I would, again, do 10.4, and then if you finish early, I would start the quiz review, or maybe take it home or something and work on it a little bit at home this weekend. Just because I don't think it's just really long, so I don't think saving it all for Monday is a smart choice, especially with so many athletes in here who have practices after school. Okay, and then your quiz is going to be, so that's everything for your quiz on Tuesday. If you guys will do me a favor, I'm going to grab out a few Lysol wipes. And if you guys could just, as you put back the colored pencils and protractors, just give them a little wipe down with these wipes, just so that, I don't know, peace of mind or something. I would really appreciate you for it. Cool? All right. You guys are like zombies today. I get that. It was a very long week, one of our only full weeks of school this semester. Just think, next weekend you'll have a 5-day weekend.
Pretty cool.
Why do we have a 5-day weekend this week? Easter?
Easter, so you have Good Friday off, Easter Monday off, and then the ACT is that Tuesday.
Why is Easter as long as spring break?
It's not.
No,
We get a whole week off.
We don't. We don't get a whole week off. We
we'll
get
technically get 3 days off instead of 5.
Oh.
technically.
Because spring break, you would have to also include the weekends, and therefore spring break would be 9 days instead of 5.
You can work at the cabin in the hall.
That's fine, leave your phones in here.
Let's go.
Oh, what's in your hand?
My hand is just so big it swallows it up.
I thought there was multiple Lysol wipes, not just one.
Wait.
Say again? So, what I just take the angles of that triangle, find that angle. On PS, this angle opens up to that arc. Oh, that's just double. Forget you. You might have been on onto something, but you might be spending a lot of time on it. I mean, not really. It's just adding and subtracting stuff from 180.
Breaking the law from having the ability to go back or up and down.
2 plus 2 is 3, but this
Kai, are
says
you working on your homework?
No, I have a question.
Would you want to North America? Would you want to North America that 2 plus 2 equals 3? Did you say so?
There was one.
I believe you.
I believe
Don't if you go, when you draw those out again, those would be considered the harm.
Yeah, I saw that.
That was impressive.
It was like, if A equals 1 and B equals 1.
Yes, it's still making you nervous that you haven't approached them at your test
Squared.
again.
Something.
1 units.
And they end up having like A equals B minus 1 by factoring.
I haven't really studied that.
He did some weird trickery in the middle, but it was
Okay.
impressive.
Do I need
But
to
it
give you a
only works
deadline
if
to get
you
some fire
subtract
under your feet?
One.
What if I told you it has to be done by next Friday?
But since they're very focused.
Maybe this weekend try and get some time to study. Oh, I need to turn this off.